Welcome to the QF channel. In this video, we provide simulation-based results that back up the theory that riding on the hoods is more aero than on the drops. We ran a computational fluid dynamics simulation to study 3 different positions: drops, hoods. As the torso was held steady, the forearms naturally assumed an almost horizontal inclination. Hoods tucked, a variation of the hood's position where the elbows are pulled closer to the torso. To allow a comparison between results, we need to isolate the aerodynamic effects of arm position, keeping the rest of the body constant across the trials. We chose an aggressive posture with a trunk angle of 18 degrees relative to the horizon. The first 2 positions are common in both training and racing, while the third is a modified posture specifically designed to reduce aerodynamic drag. For our simulations, we selected a competitive road cyclist with a naturally optimized aerodynamic position. This ensured that the observed drag differences were meaningful. A 3D scan of the cyclist in a standing position provided the baseline geometry. This model was then refined into graphics software, and a skeletal rig composed of virtual bones and joints was added. Using still frames from a video of the cyclist in the 3 riding postures, the rigged model was adjusted to accurately reproduce the dynamic positions. We then carefully corrected and smoothed the model's surface. This eliminated irregularities that arise from moving the rig, which could have skewed the results. We also included the handlebars as they significantly influence airflow, while excluding the bicycle frame to simplify the simulation and reduce computational load. For the simulations, we used open foam and assumed no crosswind and a riding speed of 14 meters per second. The results were striking. We observed a 4% reduction in total drag force when moving from the drops to the hoods, and an additional 3% reduction when adopting the hood's tucked posture. To translate these results into practical terms, we converted drag reductions into power savings. Power was calculated by multiplying the reduction in drag force by velocity, 14 meters per second. From drops to hoods, drag decreased by 0.93 Newton, which equates to a power saving of 13 watts. From hoods to hoods tucked, drag was further reduced by 0.61 Newton, and this means an additional saving of 8.5 watts. Combined, these changes saved 21.5 watts from the first to the third posture. A reduction in frontal area was the main reason for this remarkable improvement. Switching from the drops to the hoods cut the frontal area by 3.1%, because the forearms were less exposed to oncoming air. In the hood's tucked position, the area decreased by another 1.8%. Pulling the elbows in toward the torso created a more compact shape, with the arms partly covering the torso in the frontal view. The drag coefficient is calculated once the drag force and frontal area are known. The drag coefficient improved by about 1% at each change, adding up to 2% total from the first to last position. Now let's view some visual plots that support these results. The streamline plots revealed that in the drops position, the flow separated at the wrist, generating a longitudinal vortex downstream of the hands. By contrast, in both hoods and hoods tucked, the forearm flow remains smoother and more attached, without significant turbulence. On the downstream side of the arms, the airflow moved upward, creating a recirculating zone behind the upper arms. A recirculating zone forms when airflow separates from the body and loops back on itself, creating a pocket of low pressure and reversed flow, and doing this, it contributes to the creation of drag. Around the cyclist's arms, this appears as a swirl of air that circulates in place before eventually being carried over the torso of the cyclist. This zone, shown in blue in the plots, was most pronounced in the drops position and progressively diminished in the hoods and hoods tucked positions. Vorticity plots showed the formation of streamwise vortices at the wrist and elbow in the drops position. These are areas where the air spins around an axis that is parallel to the wind direction. In the other 2 positions, these vortices were either absent or greatly reduced, lowering drag. At the upper arm, the vortical structures became more complex and 3-dimensional, and they weakened as the posture became more compact. These are wake plots taken 15 centimeters behind the rider. Wrist vortices appeared only in the drops. Elbow vortices were clear in the drops, smaller in the hoods, and almost vanished in the tucked position. Upper arm vortices remained visible in the first two positions, but blended with trunk-induced structures when the elbows were pulled in. Together, these changes showed a progressive weakening and merging of arm-induced vortices, a clear indicator of improved streamlining. A view from above shows the wake behind the cyclist. It became thinner as the posture grew more compact. A thinner wake means less air is disturbed behind the cyclist, which in turn means less drag. The wake is asymmetric, with a larger part on the left side of the cyclist. This is because the left leg is extended and is the less aerodynamic of the two. This animation from the side also clearly shows the difference in the wake forming behind the first and third positions. The airflow is more disturbed after the hands and arms in the drops position, indicated by the formation of more vortices and higher velocities. These higher velocities are shown by the more orange and reddish coloring. In the end, power savings are a direct result of a reduced frontal area and improved airflow over the body, which was shown in our streamline, vorticity, and wake plots. Although these positions come at an initial cost in comfort and can be challenging to maintain, the aerodynamic benefits make the effort worthwhile. Thanks for watching. We hope this was helpful, and we're always happy to answer any questions you may have.